I wish to start from the word bits. Bits, they will say, bit refers to the periodic rise and fall in the intensity of sound, in the intensity of sound heard when two sound notes, when two sound notes of nearly equal frequencies, but similar amplitudes, are sounded together. There's a formation of bits. They can ask you to explain how bits are formed. Formation of bits. Okay? So we shall say, when two sound notes of nearly equal frequencies but similar amplitude, are sounded together, are sounded what? Together, comma, the result is the periodic rise and fall in the intensity in the intensity of sound. This is God. What? Bits. This is God what? This is God bits. Then we say, when they arrive at the ear in phase, they shall say a constructive interference takes place. A constructive interference occurs, and a loud sound is heard. Yes. That's the next point. Then the next point, okay? Next point you say, this is the first one. There are normally 3 marks. You say, when they arrive at the ear, completely out of phase, cancellation occurs. Cancellation or destructive what? Interference. interference occurs and a soft sound or no sound at all. Sound at all is what? Is heard. Is it? So here are 3 marks. When I said explain the formation of bits, or what is meant by the term bits, what is meant by the term bits, and then you see 3 marks attached. Don't just define and disappear. You'll just end up earning one mark. So what you do, you explain how bits does what? Takes place, how bits occurs. The formation of bits. Okay? Bits by definition is the periodic rise and fall in the intensity of sound. Okay? When 2 sound notes, like you have a guitar, now when you get this guitar, you are going to pluck 2 threads. When you pluck 2 threads, it is most likely that they have the similar amplitudes but nearly equal frequencies. So if the frequencies are just slightly different, then they produce beats. Where you hear something like doo, when you pluck the guitar, you hear something like doo, okay? Then the sound increases, rises, then periodically reduces. That's what you call beats. When these 2 sounding notes arrive at the ear here, and it is a crest and a crest. A crest and a crest, or a trough and a trough. They are in phase. You hear a constructive interference. That is around what? Sound. Or maximum intensity of what? Sound. And when these 2 sound notes arrive such that crest and a trough, both of them arrive at the same time. A crest cancels a trough, and no sound is heard, or a soft sound is heard. Or we can say cancellation takes place, and that is what we refer to as destructive what? Interference. Okay? Alright. Let's go to bit frequency. Bit what? Bit frequency. Okay? Bit what? Bit frequency. Of course, when we say bit frequency, we say it's the number of inherent sounds heard per second. Is the number of inherent sounds heard per second. Derivation. In the derivation, we shall say, consider 2 sounding notes or frequencies F1 and F2 respectively. Next point, if the note of frequency F2 makes one more cycle, than that of F1, then the difference in the number of cycles is equal to what? Is equal to 1. Okay? But number of cycles of frequency F1, it will be N1 is equal to F1 times T. Because we know that F is equal to N over T. Okay, if it is 1 cycle, it is 1, N is equal to 1, okay? You get it? So from that one, we can say that N is equal to F times T. Then the next one is what? The number of cycles of F what? Of frequency F2. So N2 will become F2T. Therefore, we substitute the number of cycles Substitute the number of cycles, therefore we shall now say from here that f2t minus f1t is equal to what? 1. f2 minus f1 is equal to 1 over t. But 1 over t is bit frequency, whereby t, we shall call t as bit period. As bit what? Period. Therefore, f2 minus f1 should give us our bit what? Bit frequency. That is very important equation. Very, very important. Then we shall go ahead to get 2 examples and we proceed. 2 examples. So we can simply say example. Example. Then we shall say that example, we start with the first one. 2 sources of sound are vibrating simultaneously. Vibrating, okay, simultaneously with the frequencies of 200 and 240 hertz. 200 and 140 hertz. If the speed of sound in air is speed of sound in air is 340 meters per second. Then question number 1, find the bit frequency. The bit frequency. Part 2, find the bit frequency. Part 2, what is the distance between successive locations? Find the distance between 2 successive locations of maxima. Between 2 successive locations of maximum. Locations of maximum intensity. So now here, they are asking us part 1. First, find what? The bit frequency. Bit frequency FB is equal to F1 minus F2, or FB is equal to F2 minus F1. So you can substitute. This is 240 minus 200. So we get the highest minus lowest, which gives us 40 hertz. Then they are asking what is the what distance between between the successive, not two, between the successive, yeah. So they're asking for us the wavelength. The distance between the successive maxima, that is wavelength. Okay. So part 2, F is equal to FV is equal to F lambda. So lambda becomes V out of what? Out of F. V out of what? F. So we have V at 340. We have it at 340, and the bit frequency is what? Is 40. So this will be 340 divided by 40, which gives us the distance in this case becomes 8.5 meters. 8.5 meters. Okay. Then you can also have, let's have another one. 2 tuning forks X and Y are sounded together. Number 2. 2 tuning forks X and what and Y are sounded together. Are sounded together to produce bit bit frequency. To produce bits of frequency, 8 Hz. 80 of frequency, 8 Hz. Full stop. Then we continue. Fork X has a known frequency of fork X has a known frequency of 512 Hz. Then, when Y is loaded with a small piece of when Y is loaded with a small piece of plasticine, a small piece of plasticine, the bit frequency of 2 Hz are had. Bit frequency of 2 Hz are had. Okay? Then the question says, are had when if 2 forks are sounded together. When 2 forks are sounded together. Sounded together. Full stop. Then find the frequency of Y when it is unloaded. Find the frequency of Y when it is unloaded. Find the frequency of Y when it is unloaded. So what do we say here? We shall now say that the bit frequency is equal to, we can, of course, the difference between the two frequencies, which can be f of x minus f of what? F of y. Okay? So this is 8 is equal to 5, 1, 2 minus f of y. So frequency of y will become 5, 1, 2 minus 8, which gives us what? Which gives us 5, 0 Hz. Okay? Then we say, okay, or bit frequency can be f of y minus f of x. So this is 8 is equal to f of y minus 5, 1, 2. So f of y will now become 520 Hz. Okay? Then we move on. When the fork is unloaded, the frequency of y is when the fork is unloaded, the frequency of y is 520 Hz. Since the bit frequency reduces, 520 Hz, since the bit frequency reduces. Okay? So in other words, when the bit frequency reduces, it means that the frequency of y is greater than the frequency of x. The frequency of I is greater than the frequency of x. Okay? The frequency of I is greater than the frequency of x. So therefore, from the two alternatives, you check the first one and check the next one. When you find that the frequency of y has increased, that one becomes the frequency of unloaded tuning fork. Because when you load it, in fact, when you unload it, it means the frequency has increased. So here the frequency reduces, which is not the correct. Therefore, this one where the frequency has increased. By loading it, it means you are reducing the frequency. When you load, you are reducing the what? The frequency. Unloading it, then you are increasing the what? The frequency. So we shall take that. Experiment, then you can go to uses of bits. Uses of what? Of bits. Uses of use it to determine the frequency Use it to determine the frequency of a note, and then tuning a musical what? Instrument. Okay? So we are saying that you will use it to determine the frequency of a note. Then number 2, use it to tune a musical what? Instrument. A musical what? Instrument. Use to tune a musical what? Instrument. Okay? To a given note. To a given what? Note. Now let us look at the first one. Measurement the frequency of the note. Measurement the frequency of a note. So when we ask you explain briefly how the frequency of a note can be measured, so you should be able to go ahead and what? And explain. So these are the steps you go through. Number 1, we say a note. A note is sounded together. You say a note is sounded together with a tuning fork. A tuning fork of known frequency Ft. Then next, the number of beats in time t. In time t is calculated, is counted, and bit frequency calculated, and bit frequency calculated. FB is equal to N over T. Then next, you say one prong is loaded with the plasticine, one prong of tuning fork is loaded with the plasticine, and the experiment repeated. And the experiment repeated. The new bit frequency. The new bit frequency FB prime calculated. Now, of course, in this case, we shall now say that if FB prime, if FB prime is greater than frequency of the tuning what? So FB. If these two frequencies, you find that FB prime is greater than that means that the bit frequency has increased. Okay? The bit frequency has what? Increased. That means that the frequency of the tuning fork, then the frequency of the note, then the frequency of the note is going from f of the note will be equal to f of t plus f of what? F of b. What does it mean? If the bit frequency has increases, it means that f of n is less than what? F of t. So what does that mean? It means that, in fact, it means that, in other words, that this implies that f of b is equal to f of what? N minus f of what? T. What does it mean? If the bit frequency has increased, then it means that the tuning fork has what? The frequency of the bit of the note is greater than the frequency of the tuning fork. The frequency of the note. If you see that the bit frequency increases, okay, if the bit frequency increases, it implies that the frequency of the note is greater than the frequency of the tuning fork. And if the bit frequency reduces, if FB prime is less than F what? P. What does that mean? After routing with the plasticine and find that the bit frequency has reduced, what does that mean? It means that the frequency of the note is less than the frequency of tuning what? So it will then the frequency of the note is got from, of course you shall say that is the F what? Ft minus F what? And that means that F, it will become Ft minus Fb. So you calculate from there. Then the other one, I'm giving you assignment. Go and describe how the bits can be used to tune a musical instrument to the desired what? Tone. Okay? Describe briefly how bits can be used to tune a musical instrument to the desired what? Tone. Then we shall go ahead and look at what we call Doppler. Doppler what? Doppler effect. Doppler effect. Now, you've seen scenarios where you're standing at the roadside, ambulance car comes, when it is sounding its siren, and it passes and continues when it is still sounding. What effect or what do you notice as far as the sound of siren is concerned? When the police car is sounding horn and comes towards you, there is an increase in sound. When it recedes means passing. When it has passed, it is passing, sound now reduces. You understand? So when the siren of the ambulance is coming, when the ambulance is coming towards you, you hear high-pitched frequency. High-pitched frequency. Remember, pitch depends on what? On amplitude. So you hear high sound. And when ambulance car passes, then you start hearing low sound. Until sound dies away when the police car has reached very far. And when you are standing and also the police car is standing, you notice no change in the frequency. You notice no change in the intensity of what? Sound. It remains what? The same. So that is what we call Doppler. The change in the frequency of sound is what we call Doppler. And that change should be there whenever there is relative motion between two people. The observer, the one who is hearing, and the source, the one who is sounding the whistle, for example. So we say that is the parent. Change in frequency of sound heard by an observer due to relative motion between the source and the observer. So we shall let us look at any B. Okay, first let us look at these stars. 1. Okay? We shall say that wavelength changes whenever the source is in motion. So lambda will not become change in velocity, which we call relative velocity, divided by frequency of the waves. Of course, this one comes from F is equal to lambda, V is equal to what? F lambda. V is equal to F lambda, so that's what it comes in from. That's number 1. Number 2, shall say, if the velocities are in the same direction, direction. We subtract. We subtract to get that. We subtract to get what you can say relative change in velocity, and we add if they are in opposite what? If they are in opposite direction. Like in what? For example, you can just borrow, I'm trying to borrow an idea here. Mathematically, there's a way we do it. When the body is moving with respect to another one, I want to get the change in velocity of the rest of this one with respect to the other one. There's the way we do it mathematically. But I just want to give you something simple. If you want to know more, you just go to mathematics and get more knowledge about it. So from here, we shall now start with case 1. Okay? Case what? Case 1. Observe stationary and source moving away. Moving what? Away. So in this case we shall have, let me say this is observer. Observer. Then we have the source. This is source S. The source is moving away with the speed u what? Us. Okay? So this source produces what? Produces waves. So to produce waves like this, to produce waves like that, like this, then like this. Okay? Now, since the observer is stationary, the source is in motion, we shall start with the wavelength. Apparent change in wavelength. Apparent change in wavelength will be equal to, that's the lambda prime, will be equal to change in velocity. So change in velocity will be, now this is C, this is C. So this person, this observer, this source is moving like this side. When we look at waves, so we look at the waves going to the observer. We don't look at these waves. We look at the waves going to the what? The observer. So this source is moving while the wave is sending waves behind one to the observer. So you will see that the relative change of the relative velocity of S with respect to speed of waves, they're in opposite what? Direction. So in opposite direction we add. Otherwise you're supposed to have the change like V A B. This one equals VB minus VA. Okay? Now, if they are in opposite direction, this becomes minus. Opposite direction becomes what? Minus. Which becomes a what? A plus. So we shall now say it is C plus USC divided by frequency of waves. Okay? Then, frequency apparent change. We go to here. Apparent change in frequency had by an observer, that's F prime, will be equal to, the apparent change in frequency is equal to V, first that is it. Now, since the observer is at rest, okay, so we're supposed to have the change in the velocity of the observer with respect to the what? The source. So the observer is at rest, so the only velocity we have is for the source. That is C divided by lambda. But which lambda? Of waves. So since the source is in motion, the lambda changes. Okay? So we substitute this will become C over lambda is C plus USC. Then times the frequency. That's case number 1. Then case 2. Case 2. We look at source moving towards it. What is it? Stationary what? Stationary observer. Source moving towards stationary observer. So we have the source. This is a source moving towards stationary observer. So this observer O. So the waves, this is C. So we shall start with here. We start from here and we go there, okay? So here first, we shall say apparent change in wavelength. That's lambda prime will now become, so then the same direction, what do? We subtract. So that's a C minus US, just like the other. So if there is some direction, it is velocity of B minus velocity of A divided by frequency of O. Then we go to the also to observer apparent change in frequency, that's F prime, had by the observer would be, so observer is at rest, so the only speed we have is for the waves divided by lambda, which is C divided by C minus USC times E times F. Now, what does this one mean? It implies that since this one reduces, that's what reduces. It means when you divide, this one the frequency increases. So this person here has high pitch. This person here has high pitch sound. Since frequency increases, because this one reduces, C minus US reduces, that means that it is inverse proportional to this. When this one reduces, this one increases. Then here, this one is increasing. When this one is increasing, this one reduces. This one, you say, he has low pitched, is it pitched sound? Low pitched sound, okay? Low pitched sound. Guess what? Guess what? Case 3. I'm going to look at observer moving towards a stationary source. Observer moving towards a stationary source. A stationary source. So this is source. The source S, then this observer O moving towards, that is U naught, okay? So the source gives out what? Waves towards what? The observer, the speed is that. So since the source is in motion, we shall start with the wavelength of waves, just of waves. Lambda will become C over frequency. Only because it is at rest, this one is not moving, so the other speed which is there is that one. Then we go here. So shall we look at apparent change in frequency. In what? We shall have F prime giving us, now look at this and this. They are in opposite what? Direction. So you add. That is C plus U naught over lambda, which becomes C plus U naught over lambda. So our lambda is C times frequency. So this person, of course, since this one is increasing, okay? This one is increasing, okay? That means this one also increases. This one is equal to C plus U naught increases, therefore this one also increases, because it is directly proportional. But of course, practically still you can reason these things practically. If you are moving towards a stationary what? A source, and you got to hear high pitch sound, you will. Then next, source and observer approaching each other. That's a case what? Case 4. Source and observer approaching each other. Approaching each what? Each other. So we shall have the source, then observer. So speed is US, speed is U naught, so approaching each other. This is C, speed of waves in the air. So we shall start from here. The source is in motion. Apparent what? Change in wavelength. Apparent change in wavelength. Lambda prime will now become, they are in the same direction, so it is C minus USC over frequency of waves. We go to observer, apparent change in what? In frequency. F prime will not become, this one and this one in the same, they are in the opposite direction. So in the opposite direction, what do? You add, that's the C plus U naught over frequency, over lambda. So which implies that our F prime will not become C plus U naught over lambda, which is C minus U SC times what? Times the frequency. Now, since this denominator is reducing, obviously this one has to increase. So this one is, he has high pitch sound. Okay? Then we continue. We continue. Source and observer. Case 5. Source and observer moving away from each other. Moving away from each other. So we have the source, the observer, that side, USC, the waves, that's a C. So we shall start from here. Change in wavelength, change in lambda prime is equal to, so will be V over F. F is equal to V is equal to F lambda. So it is change in velocity over frequency. So change in velocity, so that will be C in the opposite direction. So you subtract. You add plus USC over frequency of the waves. Then apparent change in what? In frequency. That's F prime. Will not become what? F prime, so they are in what? In the same direction, we subtract. That is C minus U naught divided by what? By lambda prime. So F prime will not become, we substitute C minus U naught over C plus USC times what? Times F. Now, since this one reduces, since denominator increases, then the frequency reduces. So here is low pitch what? Sound. Because this is a proportion, like though you say pressure maximum, area minimum. Pressure maximum, area minimum. So in general, in what? In general, apparent change in wavelength. Apparent change in frequency. That's F prime will become, so it is C plus or minus U naught over C plus or minus USC times the frequency of the waves. What does that one mean? It means that if the observer is stationary, this one is 0. If the observer and the waves are moving in the same direction, then we shall use minus. If the observer and the source, if the observer and the waves, okay, if we look at the speed direction of the waves and that of observer, should they be in the opposite direction? You add. So the same thing here. If the source and observer are in the same direction, so if the source and the speed of waves, if the source and waves are in the same direction, we simply use subtraction sign. If the source and the waves are in the opposite direction, we simply add their speeds. This one applies to the calculations. Is that okay? Applies to the calculations. So, in the next one, in the next lesson, we shall come back with the applications of Doppler plus very many examples. So, as per now, let us first pause there. We are coming back. We are coming back with examples and look at the applications of Doppler. Where do we find the concept of Doppler in our day-to-day life? Is that okay?